Okay, let's review this problem. We solved the first two, the relative humidity at the exit and the power input to this compressor. So to solve the first problem, we use the conservation of mass principle. That means that the amount of air at the inlet is the same as the amount of air at the exit, and the amount of water vapor at the inlet is the same as the amount of water vapor at the exit. That means the mass of water vapor divided by the mass of dry air is the humidity ratio omega. So from this, we can learn the humidity ratio omega is the same between the inlet and the exit. So we use this equation to determine the relative humidity at the exit. First, we know the relative humidity at the inlet, which is 70%. So we use this equation, PV is PG. Again, in the relative humidity is PV over PG. By the way, this PG is P set, the saturation temperature at the given saturation pressure at the given temperature. So the inlet temperature is 50 degrees Celsius. So if you find saturation pressure at 50 degrees Celsius, we get this value, 0.1235. That is P set at 50 degrees Celsius, which is the denominator in this equation. Since we know the relative humidity is 0.7, if you multiply this 0.7 by P set, you can determine PV. Once you know PV, we can determine humidity ratio omega, because omega is 0.622 PV over P minus PV. In this equation, we can use this equation at the inlet, which is number 1. So PV1 over P1 minus PV1 is going to be omega. And we already calculated PV1, which is 0.08645. We can use this equation, and we can use this value here, PV1, and here, PV1. By the way, P1 is the total pressure at the inlet, which is 0.9. So we have all these three values, then we can determine omega, which is a humidity ratio, 0.0545. Based on this conservation of mass principle, we know omega 1 is the same as omega 2. So omega 2 is going to be 0.0545. Then using this value, which is 0.545, we can use the same equation, 0.622 times PV over P minus PV at the exit, number 2. So 0.0545 is 0.622 times PV2 over P2 minus PV2. And the exit pressure, P2, is given here, 1.5. We have everything but PV1, so we can determine the partial pressure of water vapor at the exit. From this equation, the partial pressure of water vapor at the exit is going to be 1.1441. Then using this using this partial pressure, we can use the same equation as given here. Phi, the relative humidity, is PV over PG for the exit. So phi 2, the relative humidity at the exit, is going to be PV2 over PG2. PV2 is given from here, and PG2 is the saturation pressure at the given temperature at the exit, 195. It is 14.04. So we have everything but relative humidity. So we can determine the relative humidity at the exit, which is only 1%. from this, from this solution, we can learn that, we have the same amount of air, same amount of water vapor at the inlet, at the exit, but because of the temperature increase, because of this temperature increase, the relative humidity for the same mass of water vapor can go up from 70, can decrease from 70% down to 1%, because when you increase the temperature, the amount of water vapor can be present in air can increase dramatically. So here the partial pressure is 14. On the other hand, the partial pressure at the inlet is only 0.1225. So you can see there's a dramatic increase in the saturation pressure due to the temperature increase. Because of this, air can contain more moisture, but the moisture amount is limited, is the same. That's why the relative humidity drops from 70% down to 1%. This is why we use a humidifier in winter, because we use a heater for the same amount of water vapor, the same amount of air in the house. However, since you are increasing the temperature, the relative humidity can drop from this much and down here. So that's how we solve the part one, the relative humidity at the exit. The second problem is the power inlet, power input. To determine this power input, we need to use the energy balance equation. So we started from the general energy balance equation for steady state open system, and we reduced this energy balance equation down to this one. I'm sorry, down to this one, which is for this compressor. So this compressor, this equation shows that the power input to the compressor plus the rate of enthalpy at the inlet should be the same as the rate of enthalpy at the exit. This is what we learned in Thermodynamics 1. In Thermodynamics 2, we use air as moist air, which means that the rate of enthalpy H dot can be determined by m dot of A times HA plus omega, which is the relative humidity, humidity ratio times the specific enthalpy of water vapor. So instead of H for the inlet, H for the exit, we use this one for the inlet right here. We use this one for the exit right here. So we converted this equation down to this one. And this is the unknown, which is the power input. We just need to determine each one by one, each the term one by one. To determine the mass flow rate, we used this ideal gas equation, and we have this ideal gas equation can be rewritten as this form, is this rate form. So you can see flow rate, volumetric flow rate, and mass flow rate. This mass flow rate was determined by using this equation, since we know the partial pressure of air and the flow rate, which is 0.8, which was given in the problem right here. And the gas constant of air can be determined by this equation. By the way, if you solve this equation, you get 0.287, and the temperature is going to be at the inlet, which is 50 degrees Celsius. However, we have to use Kelvin, so we use 323 Kelvin. For this partial pressure of dry air, we can calculate this partial pressure of dry air from the partial pressure of water vapor. The partial pressure of water vapor is 0.08645 out of 0.9. So the partial pressure of the other component, which is dry air, can be determined by 0.9 minus 0.08645. That is the partial pressure of dry air at the inlet, which is this one, 0.81355. So we can use this value for the partial pressure of dry air, and we know the flow rate we know the gas constant and temperature, so we can determine the mass flow rate of dry air, which is 0.702. We already know omega 1 and omega 2. We determined omega 1 and 2 from the previous analysis. Omega 2 is 0.0545. Omega 1 is also the same, 0.0545. So we have this omega. HA1, HA2 can be found from this ideal gas properties of air. So we can find HA1 at the inlet temperature, which is 323 Kelvin. So we can do a linear interpolation between these two numbers. And the answer is 323.3. At the exit, the temperature is 195, which is 468. So we can do a linear interpolation between these two numbers to determine H value at 468. The specific enthalpy is going to be 470, which is written right here, 470. And HV and HV at the inlet, HV at the exit can be found from this table A23. So this is table A23. However, this property is in kilojoule per kilomole. So once you get the value in kilojoule per kilomole, you need to divide by kilogram per kilomole, which is the molecular weight, capital M. Then kilomole can be cancelled. We get the specific enthalpy in kilojoule per kilogram. So we can find H bar, which is the specific enthalpy on a molar basis at 323, which is this one, 107.40, and we can do it at 468 between these two numbers. That is 15707. We need to divide this by the molecular weight of the system. By the way, the molecular weight of water is 18.02. So you can divide this value by 18.02 to determine HV1, and you can do the same for HV2. Then we have everything. You can determine the power input for the compressor to be 115.9 kilowatt. That was the second part of this problem. The last one is the rate of entropy production. To solve this rate of entropy production, we need to come up with this entropy balance equation, which is given here. We first assume that this is a steady state. Therefore, we can neglect time-dependent term on the right-hand side. And we want to determine the rate of entropy production rather than just entropy production. So we have to divide this entropy production by time t. So that's what we did. If you divide by time t, we get the rate of entropy generation, which is the rate of entropy production. They are the same thing. It's going to be m dot times the specific entropy at the exit minus the specific entropy at the inlet. By the way, specific entropy of moist air should be evaluated in this way as A plus omega times SV. So we use this one, multiply by m dot of A. So we use this term to represent the entropy at the inlet, the entropy at the exit. So you can see the same thing here and here. Now, m dot A is the same because it's a constant flow rate. There is no, we only have one inlet and one exit. So we have the same flow rate, mass flow rate at the inlet and the exit. So we can take this one out, which is 0.702. out of this equation, and we can combine SA2, which is the specific entropy of air, SA1, these two together like this, and these two together like that. And we can use the entropy equation that we studied in EGR456 in chapter 6. The equation S2 minus S1 is S degree 2 minus S degree 1 minus R natural log P2 over P1. So we can use this term to solve SA2 minus SA1, SV2 minus SV1. So instead of SA2 minus SA1, we are going to use this term as a degree minus S degree A1 minus gas constant R, which is universal gas constant divided by molecular weight, which is given right here, and natural log PA2 minus PA1, and we can do the same, natural log PV2 minus PV1. Then, where can we find this S degree for air and S degree for water vapor? We can go back to this equation, and we can go back to table A22 to determine S degree. We can do a linear interpolation between these two numbers to determine S degree at 323. Let me give you the value S degree at 323 Kelvin. If you do a linear interpolation, we get 1.77625. We can do the same, doing linear interpolation between these two numbers to evaluate S degree at 468, which is the exit temperature. S degree at 468 Kelvin is going to be 2.15165. Similarly, we can find S degree at 323 at 468. Let's do that. But this one is not just S degree, which is S degree bar, which means that on a molar basis. So if you want to evaluate just S degree, you need to divide by molecular weight. The same goes to 468. Anyway, S degree bar at 323 is going to be 191. So we are doing linear interpolation between these two numbers. 191.409 and S degree bar at 468 Kelvin. So this one is at 323 Kelvin. Is linear interpolation between these two numbers. We get 204.097. So we can use these values here in this equation, as A1 is this one, 1.77625, as A2 is this one, 2.15165, as V2 is this one, 204.097. However, this is S degree bar. So if you want to remove this bar, we need to divide by molecular weight. By the way, the molecular weight of water, because this is a vapor, water vapor, it's 18.02. So divide by 18.02. We can do the same for the inlet, which is 191.409. 191.409 divided by 18.02. Now, finally, PA2 minus PA1, the ratio is going to be 1.9, 1.5 divided by 0.9. The same goes here, 1.5 divided by 0.9. So if you solve this one, you get the rate of entropy generation, which is 0.182 kilowatt per Kelvin. Okay, so that's how you solve this problem. The governing equation is not very difficult. We are just using the same equation that we learned from EGR456, the thermodynamics 1. However, each term for air, we use this one to account for the effect of dry air and the effect of water vapor. That's what, it makes, it may look complicated. However, the only difference is this term. We are just using the same equation that we learned from thermodynamics 1. Okay. Of course, to evaluate each term, we need to look, use a number of linear interpolation to evaluate the property at a certain temperature. But in your exam, I will do my best to minimize the linear interpolation so you don't waste time during this process. Okay, but this one is an example, so you need to learn how to solve a problem without any simplification. Any question about this problem? If I give you this problem in your exam 1, can you solve it? Of course, the exam problem will be shorter than this one to save your time, because this one takes a lot of time because we have to do a lot of linear interpolations. However, in the exam, I may provide the exact temperatures rather than, the linear interpolation. That will save a lot of time. Okay. That's one example. Before we solve another example, there's one thing that we need to study, which is called dew point temperature. Dew point temperature is the temperature when water condensates. So in winter, when you use a lot of heater in your car, sometimes you have a foggy windshield. The reason is because of this dew point temperature. So let's learn about that. So what's going to happen is, so this is a car. There's a windshield in front. So let's say, that the windshield outside temperature is very cold. Let's say minus 20 degrees Celsius. Inside, we are using a lot of heater. So 20 degrees Celsius. At this 20 degrees Celsius, there is this air inside this cabin contains moisture. That means sometimes, it may contain a lot of moisture. Therefore, it has a high relative humidity. Or sometimes, it is dry, so the relative humidity is low. However, you can determine what is the maximum amount of water vapor can be present in the air inside by just checking the relative humidity equation, which is this one. Phi, which is the relative humidity, can be determined by PV over PG. This PG is P set at the given temperature. So how can we determine P set at the given temperature? You can go to temperature table, which is table A2, temperature table. This one, and what is the temperature inside? 20 degrees Celsius. So let's find P set at 20. There's a 20 degrees Celsius here. P set is going to be 0.02339. However, this pressure is in bar. So in kilopascal, this one is 2.339 kilopascal. Then, depending on the amount of the moisture inside, let's say the relative humidity is 50%. That means that the humidity ratio, the PV, the partial pressure of water vapor, is going to be just half of this one. So it's going to be 1.1695 kilopascal. So that is going to be the partial pressure of water vapor. That is what we learned last week, how to determine the relative humidity or water vapor from this relative humidity or the other way. If we understand this, the situation on a PV diagram and TV diagram, TV diagram, let's say the temperature is 20, so this is 20 degrees Celsius. Then what we have, TV diagram looks like this. And we can make another TV diagram at lower pressure. This pressure is going to be P set 2.339 kilopascal. And this pressure is going to be the actual pressure here, 1.1695 kilopascal. And we have this saturation curve, saturation line, looks like this. So water vapor in air is superheated vapor. So that means that water vapor in air should be only here. Only here. So on the right-hand side. Because if you look at this curve, TV diagram, here is compressed liquid. This point is saturated liquid. Here is a saturated mixture. Here is saturated vapor. And this one is superheated vapor. Presently, the temperature inside the cabin is 20 degrees Celsius. That means our system is supposed to be somewhere on this line because temperature is 20. If our system is at 30 degrees Celsius, we are supposed to be somewhere here. If it is 10 degrees Celsius, somewhere down here. However, the temperature is 20. That means that on this TV diagram, air in this water vapor in here should be on this line. But the water vapor in air should be superheated vapor. Always superheated vapor. So the system is supposed to be on the right-hand side, outside of this saturation line. So this is only possible water vapor of the air inside this cabin. And the partial pressure is 1.1695, which means 1.1695, this is our system. Presently, our system is right here at this point. For the same temperature, if you add more moisture into the air in the cabin, this one is going to move this way. And when it hits this number 4, that is when the relative humidity of the air inside the cabin is going to be 100%. So this is when relative humidity phi is going to be 100% at 20 degrees Celsius. So if this point moves to the left, that means relative humidity phi goes up, and 60, 70, 80, 90, and 100%. So beyond that, it's not superheat vapor anymore. We have saturated mixture, means liquid and vapor together. So beyond this point, we don't have pure 100% vapor. We have liquid, means that condensation. So moving this way means that you are adding more moisture. Moving this way means that you are removing moisture. What about if you do not add or remove moisture? On what direction this water and this, the water vapor can move if you do not add or remove moisture? The partial pressure is not going to change. If you increase temperature, this one moves this way. If you decrease temperature, this one moves this way. So if you can add or remove moisture, if you add it, this one moves this way. If you remove it, this one moves this way. So this horizontal line represents relative humidity phi. If you do not change the mass of water vapor, then the only way this, the water vapor can move is up and down on this partial pressure. So if you decrease the temperature of the cabin, it's going to move downward. And eventually, it will meet this point at a certain temperature. So what is the temperature? It is approximately, I don't know the exact temperature, but let me give you the approximate value. It's going to be around 14. 1.16, 1.7. It's going to be 9 degrees Celsius, approximately. Approximately, okay? So if you decrease the temperature inside the cabin down to 9 degrees Celsius without adding or remove moisture, the water vapor is going to hit this point, which is 1, 2, 3, 4, 5, saturated vapor. Below this temperature, you don't have 100% vapor. Now you have condensation, because this is only when you are here, that's when you have 100% vapor. When you cross this saturation line, that means that you have a liquid water. So outside is minus 20 degrees Celsius. The windshield is going to be at low temperature, let's say minus 10. Then what will be the temperature around windshield? What will be the temperature, the air temperature around windshield? It's not going to be 20 degrees Celsius. It is very close to this windshield, which is at minus 10 degrees Celsius. So let's say it is 8 degrees Celsius. Then, where is 8 degrees Celsius? On this line. Cannot be here anymore. So it's going to cross this saturation line. That means that there should be condensation. When temperature go beyond this temperature, 9 degrees Celsius. So what is this 9 degrees Celsius? Dew point temperature. So if the air is above this dew point temperature, you have 100% superheated vapor. However, below this dew point temperature, you have a liquid water. The reason why your windshield is going to be foggy is because of the condensation of water on the windshield. So it's not water vapor anymore. It is a liquid water droplet, which is too small. That's why it looks like a foggy, the windshield on your eyes, because the temperature on the windshield is below dew point temperature. So if that happens, what we need to do to remove this, the foggy, the windshield, we can. So we need to move, we need to go, go cross this, the saturation line again. So what we can do is that we can remove water vapor by using air conditioning system, or we can increase the temperature even higher than 20, maybe 30 or something. So this temperature near the windshield can go above this dew point temperature. So we can increase the temperature of the air, or we can remove water vapor by using air conditioning system. And if you use the button that remove the foggy window, it runs air conditioning system to remove water from the the water vapor from air, and it also increases the temperature inside the cabin. That's how it removes the foggy window. Okay. So this one explains, how this dew point temperature works. So it has everything about what is written here. Okay, make sense? Okay. So based on that, so that's the physics. That's how this dew point temperature works. And let's talk about mathematics. Once you understand this dew point temperature, now we need to solve this using our tool. What tool do we have? Mathematics. So how can we use this dew point temperature? Below the dew point temperature, we know there is a condensation. That means that liquid water is going to form from water vapor. So if we say this is the inlet where the water and air mixture, which is moist air, enters at number 1, let's assume that there's a condensation occurs. Then we have exit here. So this is exit number 2, exit number 3. This is, the where condensation comes out. So there's a liquid water. And the remaining moist air is going to be removed from the system through exit number 2. So what kind of, the equation we can use? We can use conservation of mass principle. The amount of liquid water should be from the amount of, the water vapor from the moist air. So if we consider the conservation of mass principle for water only, so at this inlet, we have mass of dry air and mass of water vapor together. So since it is inlet number 1, let's say MA number 1, MV number 1, and some of this water vapor is going to condense in this system. So it's going to be removed. The amount of liquid water is going to be M of W. Then at the remaining moist air, MA plus MV is going to be removed at the exit number 2. So this is exit number 2. So I'm going to say MA2 plus MV2. So let's apply conservation of mass principle. So we assume that there is no chemical reaction or nuclear reaction. So the air cannot be water, or water cannot be air. So the amount of air should remain constant. The amount of water should remain constant. Between 1 and 2, we have mass of dry air, MA number 1. What is the relation between MA1 and MA2? Since there's no air at number 3, the mass of dry air at the inlet number 1 should be the same as mass of dry air at the exit number 2. So MA1 is the same as MA2. What about water vapor? We have a water here, water here, water here. So there's only one water goes in at number 1, and there are 2 waters come out at number 3 and number 2. So mass of water, which is vapor at the inlet number 1, should be the same as mass of water, which is the condensate at number 3, plus the mass of water vapor at the exit number 2. So these two are mass balance equation. If we move this one to the left-hand side, move this one to the right-hand side, we get this equation. M of condensate is the same as MV2, I'm sorry, MV1 minus MV2. If you divide, by the way, the mass of dry air is constant, so we don't have to, separate into 1 or 2. We can just say M of A. If we divide this by M of A, M of A is the same as MA1. M of A is the same as MA2 because the mass of air is conserved. By the definition of omega, which is mass of water vapor divided by mass of dry air, this is going to be omega at the inlet number 1. This is going to be omega at the exit number 2. So mass of condensate divided by mass of dry air is going to be omega 1 minus omega 2. So we can use this equation when we have a condensation. Any question up to here? So this is the new equation we studied. Which one? This one? This one stands for that the mass of the water remains constant. So mass of water vapor goes in, should remain, should be removed from the system, which is this one. However, instead of this one, using omega is much simpler mathematically. So we convert this one into omega. Omega has no unit, mass of water vapor, so it's going to be kilogram. Mass of dry air, it's a kilogram, so you can cancel them out. Then let's solve this. So we are talking about removing water vapor from moist air. So what kind of system is it? It's a dehumidifier. So the next system we are going to study is going to be dehumidifier using this dew point temperature. Then how can we solve this dehumidifier in energy balance equation? So basically, to have the condensate, we need to reduce the temperature of the system. If you don't remember, please look at this, the example, because of the temperature decrease near the windshield, and the temperature becomes, the temperature becomes lower than this dew point temperature. That's when condensation occurs. So to remove water from moist air, we need to decrease the temperature. So in this example, we have a cooling system. cooling coil is connected into this dehumidifier. So we have one inlet number one exit, exit number 2. We have another exit for condensate, which is number 3. And using this cooling coil, we are removing heat. There's a Q out. Since it's an open system, one inlet, two exits, it is convenient to use a rate form. So instead of Q out, we can say the rate of heat transfer Q dot out. To solve this one, this dehumidifier by energy balance equation, we need to make some assumptions. The first of them is at the inlet number 1, moist air enters. If the dry air enters, there's no condensate, so it is simple to understand. As the moist air flows over the cooling coil, some water vapor condensed because the temperature T goes below the dew point temperature. And saturated moist air exits at state 2. So our assumption is that the relative humidity at the exit number 2 is going to be 100% because there is a condensation. Means that the dew point means that the relative humidity inside this dehumidifier is already 100%. And finally, the condensate exits as a saturated liquid. So our assumption is that condensate is phase change process number 2, saturated liquid at the same temperature between number 3 and number 2. So there's no temperature gradient between number 3 and number 2. So these are the assumptions that we are going to use. Then based on that, let's talk about mass balance first. Mass balance is the same as what we discussed already. So we have mass of air and mass of vapor together at the inlet number 1. And since we are using, the rate form, whenever we have a steady state open system, we use a rate form. That's what we studied, EGR456, chapter 4, right? And it's a flow rate. So instead of MA, we are going to say M dot of dry air plus M dot of water vapor at the inlet number one. And some of water is going to be removed from the system as condensate, means that there's a condensation. And the amount of the mass flow rate of condensate is going to be M dot of W, which is from M dot V1. So, and the exit number 2, we have a moist air, M dot A plus M dot V again. Using the rate form, it's going to be M dot A, M dot V. This is exit number 2. I'm going to add number 2 here, number 2 here. So if we use a conservation of mass principle for dry air, we only have dry air here and here, just 2. One is at the inlet, the other is at the exit. So this one should be the same as this one, which is pretty simple to understand. M dot A1 is the same as M dot A2. So there is no difference between M dot A1 and A2. Let's just say M dot A. What about water? We have water here, water vapor at inlet number 1, water here, liquid water at number 3, and water vapor at number 2. So this one should be the same as the sum of this one and this one because we only have one inlet, two exits. So M dot of water vapor at the inlet should be the same as M dot of water vapor at the exit number 2 plus the condensate. Then from this equation, M dot of W is m dot v1 minus m dot v2. If you divide this by m dot of A, by the definition of humidity ratio, omega is m dot v over m dot A. If it is omega 1, m dot v1 divided by m dot A1. If it is omega 2, m dot v2 divided by m dot a2. So if we say this one is 1, this one is 2, we can do that because they are the same. This one, m dot w over m dot a is going to be omega humidity ratio at number 1 minus humidity ratio at number 2. So this is the governing equation for mass balance. Any question up to here? Not much. One last slide. Then what about energy balance? How can we use energy balance for this dehumidifier? It's we have one inlet and two exits. So if you do not know how to make the energy balance equation, always start with the general energy balance equation, Q dot in. By the way, this is a steady state open system. The energy balance equation can be found from chapter 4, Thermodynamics 1, plus W dot in plus M dot at the inlet. What is the inlet? Number 1. And this one has enthalpy, kinetic energy, and potential energy. And we have two exits, number 2 and number 3. So first, number 2, this one has enthalpy, kinetic energy, and potential energy. And we have another exit, number 3. This one has enthalpy, kinetic energy, and potential energy. And we can neglect kinetic energy change and potential energy change. And there's no energy transfer by work. And there's a heat loss from the system by using this cooling coil. Heat loss, Q out. If there is a Q in, will there be condensation? Of course not. When you increase the temperature, the system temperature goes away from the dew point temperature. Only one occasion when we have a condensation is when the temperature of the moisture air go below the dew point temperature. So to decrease the temperature of the air, we need to remove heat. So we always have Q dot in dew humidification. And that means that we don't have Q dot in. We already have Q dot out. And this one is just H dot number 1. Instead of M dot 1, H1, because we have an air and water mixture. So it is convenient to just use this capital H rather than M dot 1, M dot 2, because we are going to use another form to represent this one. That is, H is MA HA plus omega HV. If you don't remember, you can go review. This slide. This big H is going to be MA times HA plus omega HV. Anyway, so we have H1, we have H dot 2, we have H dot 3. So we have Q dot out here. So this is our energy balance equation. But we don't want to use the energy balance equation as is. We want to use this form. H is MA HA plus omega HV. Because we have moist air. When we have moist air, this is the equation. Then this one becomes MA1. Oh, we have a dot on top of it. So M dot A1, HA1 plus omega 1 HV1 is Q dot out plus M dot A2 HA2 plus omega 2 HV2 plus this one, number 3. If you go back to this schematic, we have moist air. So we have MAMV at the inlet number 1. We have MAMV at the exit number 2. But in exit number 3, we only have water only. So we don't have to use this one. For number 3, we can just say M dot of condensate, water, times H of water. So this is our energy balance equation. So if we solve this one, we can determine any unknown in the system. By the way, from the previous mass conservation, this M dot of W is the same as M dot A times omega 1 minus omega 2. Okay? So that's everything. And also we studied M dot A 1 is the same as M dot A2. Where is it? Dehumidifier. Dehumidifier. So the mass balance equation M dot A1 is the same as M dot A2, which is M dot A. So we can remove subscript here. Yes.
That H time at the very end of the energy balance equation, is that minus H times W or H, was it minus H sub W?
Where's minus? Oh, that is times. Times. HW, the specific enthalpy of water. This equation is shown here, right here. So if you compare these two, we have M dot A comes out of this side. So we have M dot A divided by M dot A. Then we get the same equation. So this part is here. This one is here. This one is here. And the last one, which is this one multiplied by H of W. And this one is here. So you can also use this energy balance equation, the same thing. So that's everything. And we are going to solve one problem to study dehumidifier. And the next one is, the psychrometric chart. That is just for your reference. So the exam is going to contain only the dehumidifier using this energy balance equation and mixing chamber using the energy balance equation and the compressor. So we solved 3 problems, one for mixing chamber and compressor and this dehumidifier. So in your exam 1 for this chapter 12, you are going to see one of these 3, maybe 1 or 2. And the similar questions will be asked, like the using please use the mass balance equation to determine any unknown, or energy balance equation to determine any unknown, or entropy balance equation to determine the rate of entropy production. So what you are going to see in your first exam is nothing different from the problems that we solved together in the classroom. So start with solving these problems first and then go to your homework assignments and so on. You will learn that each problem takes a lot of time, because even this energy balance equation, we have many terms and each term requires a lot of effort to determine that. Okay, so but in your exam I will do my best to simplify them, but it still means that you need to practice a reasonable amount, otherwise you will run out of time in exam 1 for sure. I can guarantee you that that if I give you 4 hours for the exam, everyone can get 100%. So the question is going to be whether that you are familiar with solving these problems or not, because that you will use the same energy balance equation in the textbook, the same energy balance equation in this PowerPoint. So you will write the energy balance equation, and there are slides for each term. So if you go over all the slides, you will learn how to determine each one by one. However, the time is limited, so you need to be able to solve them rather than just learning from your formula sheet or something. So it is important for you to practice these problems as often as possible. And one thing for sure, each problem takes a lot of time. It's not as simple as Thermodynamics 1. It's advanced thermodynamics course, a little harder than what you used to see. So let's look at the first problem, this dehumidifier.